Okay, so we're going to take a look at yet another circular motion problem. This one's going to be a little bit more interesting. This is going to be a lot like the group problem we looked at, where we're looking at a satellite in orbit around the planet Earth, and we're going to be treating it as though it's moving in a perfectly circular orbit. So, a satellite moves in a circular orbit around the Earth at a speed of 6.6 kilometers per second. Determine the satellite's altitude above the surface of the Earth. Assume the Earth is a homogeneous, in case you want distinction on pronunciation there, a homogeneous sphere of radius 6,370 kilometers and has a mass of 5.98 times 10 to the 24th kilograms. The value of the universal gravitational constant is 6.67259 times 10 to the negative 11th with its slew of units, as we either have or will discuss in class. All right, there are a few things in here that are worth noting. For Gen Physics, this is just a little bit of housekeeping. Don't let it throw you off when it says assume the Earth is basically what they're saying there is, we're going to say that the Earth is just nice and uniform and it's just a ball floating in space. Now in real life, it's not a perfect sphere, which would throw this off ever so slightly, but this, as you'll see, this is actually a pretty good approximation, at least for the level that we are working at. Now, of the things that they give us the following. Yeah. Speed of the satellite. Speed of the satellite is 6.6 kilometers per second. That is common, as you either have seen or will see. When we're dealing with stuff in space, it can either be moving incredibly fast or incredibly slow. It can be kind of all over the place. This is 6,600 meters per second. As we've talked about before, we want to convert everything into the SI system for our calculations. It makes our lives much easier. As we go forward from here, you're going to see that if you put it in the wrong units, you get weird results. While it may not seem useful to have a larger number like this, these are the SI units, so when I put SI in, I will get SI out. The mass of the Earth. Let's see, Earth, I believe, has the little cross there. I need to brush up on my symbols. But the mass of the Earth is 5.98, according to this problem, times 10 to the 24th kilograms. Now, as a reminder, this is the same thing as writing 5.98 times 10 raised to the 24th kilograms. But as I have mentioned in class before, I much prefer using the engineering notation because it keeps the important number, 24, big and in your face, as opposed to this notation, which makes the important number tiny and easy to overlook. You may use whatever you'd like, of course, so long as you use it correctly and I can understand what you're saying. They say that the radius of the Earth is equal to 6.370 times 10 to the 6th meters. They gave us 6,370 kilometers. I am converting that for you into meters. It is 6.37 times 10 to the 6th meters, because kilometer is already times 10 to the 3rd. Then we had 6,000 of those. All right. The universal gravitational constant is 6.67. They give you 259, but that's fine. Times 10 to the negative 11th. Its units are Newton meters squared per kilogram squared. All right. So this is the information that they give us. They want the following. Let's draw a picture of this. Here's the Earth. Happy little Earth. And then we've got a satellite. The satellite is going in a circle of some radius r. Let's go with, actually let's call that lowercase r, so that we don't confuse it with the radius of the Earth. All right. And they want to know the following. Determine the satellite's altitude above the Earth. So we're almost looking for r. We definitely want to know r, but what r is from the center of the circle, which is actually at the center of the Earth. When they say altitude, that usually means above the surface of the Earth. That's why they gave us the radius of the Earth. We'll deal with that at the end. It's not normally the sort of thing that I insist upon. That's more of a small distinction that I usually reserve for my AP classes. But this was a pretty good problem, so let's take a look at it. All right. Here's where things get a little bit tricky. We're dealing with something moving in a circle, and anything moving in a circle must have a centripetal force. The way that I've drawn it here, and this is a great freeze frame, I'm going to draw a free body diagram. I have, the way that I've drawn it, there's a force of gravity that is pulling the satellite towards the Earth this way. Oh, let me change my notation. It's been so long since I've done that. Now that's a capital G, because this satellite is not near the surface of the Earth anymore. It's actually up in orbit, which means our old equation, F little g equals mg, is not going to help us here. Or at least not the way that we normally go about things. You can also use you could find the local little g at this distance, and you could use that. The problem is, we don't know what that distance is what we're trying to find. Let's look at the forces acting on this guy. So we have sum of forces in the way that I've drawn it in the x. I could have drawn it with the satellite up here, it could have been in the y, or down here, or pretty much anywhere. But I'm going to take this just simply. I've also got it pointed to the left here, so I could call that negative, so I'm going to call that negative F capital G. And that's it. That's my only force with it out in space. There's nothing holding the satellite up. It's actually falling towards the Earth, but it's moving. It has some velocity. In fact, 6.6 kilometers per second. It's moving so fast that by the time it would hit the ground, it's actually moved over here. It's constantly falling around the Earth. That's what an orbit is. This is also why I don't like calling the force of gravity the weight, because we would identify astronauts or cosmonauts on this satellite, if they were working on it, as weightless, but they do have a force of gravity on them. In short, we're setting that equal to my centripetal force, which needs to point towards the center. That's actually going to be negative Fc. Negative because the way that I've drawn it, it's also pointed to the left. Centripetal always points to the center of the circle, well then my centripetal force would actually point that way. It's nice because the negatives cancel out and we end up with the following. In short, this is a statement that says that my force of gravity from the Earth is my centripetal force. Okay, well here's where we need to bring in the universal gravitation equation. This was Newton's law of universal gravitation. It's capital G times mass 1 times mass 2 divided by the distance between them squared. We've got a force of gravity between the Earth and the satellite, which we don't actually know the mass of. I'm just going to call it m. And the distance between them, r squared. Now remember, that's the distance between the center of them, so the center of the Earth to the center of the satellite. Now, we do know this, that's the mass of the Earth. We do know this, the universal gravitational constant, and we want this. We also know that the force of gravity must be equal to the centripetal force. I know many of you may not like me using just variables on this, but you're going to see why this is useful. I have not given you, well, this problem has not given you the mass of the satellite. So many of you may run into a problem where you think that you don't have enough information to solve, but when you write it out like this, you can see I have a mass term on both sides. The mass of the satellite is actually irrelevant. It drops out of the equation. I don't have to give you a mass. And r, well, I can multiply both sides by r squared, and I get the following, because I'm trying to solve for r. I get g mass of the Earth equals v squared times r. Now I divide both sides by v squared, and I get the following. Once again, we're starting to get close to a general solution on this, because you'll notice I haven't filled in any of the numbers that my problem gave me, which means this is helping you out even more than the usual stuff that I do in these videos. Because at this point, you can just start plugging in numbers and getting the result. Once again, if you simply write this on an exam, you get almost no points. I need to see you drawing these connections. Free body diagram, Newton's laws of motion, incorporating the idea that your gravitational force is equal to your centripetal force and working together based off of that. But this is actually accurate. In fact, and we either have or will have talked about Kepler's laws of planetary motion. Kepler's third law, if I do a little bit more replacement on this, where I replace the velocity with the period and the circumference of a circular orbit, is the approximation we end up using. That's how you get the relationship between the semi-major axis and the period. This is actually how you derive Kepler's third law of planetary motion. It's one of the things that Newton actually figured out by applying all of this stuff. No one knew why Kepler's laws worked, they just knew that they did. Newton explained them. We're pretty much done. R equals g times the mass of the Earth divided by the velocity of the satellite squared. At this point, here's the beauty of solving things with variables. All of you are done, right? You don't have to go through and replace everything with your numbers. You literally just put in your numbers here. So, g, we said, was 6.67 times 10 to the negative 11th. Now, here comes the mess of units. Newton, meters squared per kilogram squared, okay? Times the mass of the Earth, which we said was 5.98 times 10 to the 24th kilograms. And then divided by my velocity, which we said was 6.6 times 10 to the third meters. That's 6,600 meters per second. I apologize. Quantity squared. The whole thing needs to be squared. All right. Here's where some of the difficulty comes in. You got to put in big numbers into your calculator. Now, hopefully you're getting some practice with this, because on the exam, I'm going to expect you to be able to do this. Times 10 raised to the negative 11. Many of you are probably even better at this than I am. I just put it in the way that I know how to. All right, if I've done this correctly. The radius for our orbit, this distance here, r, that is from the center of the satellite to the center of the Earth, is 369.157 times 10 to the 6th meters. Here's where that last step comes in. They ask for the altitude above the surface of the Earth. So if I were to actually draw this more to scale, I've got the Earth here, and it has a radius, here's that radius that they gave us, of 6.37 times 10 to the 6th, I think. I'm going off of memory here. Actually, my memory of the actual value, not what was given in the problem. Yeah, 6.37. 6.37 times 10 to the 6th. And we found that the total distance out to the satellite is 9.157 times 10 to the 6th meters. So if I want to find the altitude above the surface of the Earth, that's this guy here. So the altitude is going to be 9.16 times 10 to the 6th meters minus 6.37 times 10 to the 6th meters. So I subtract those two. It's basically 9.16 minus 6.37. We come up with the following. It is 2.79 times 10 to the 6th meters, which is the same thing as 2,790,000 meters. Let me see what they actually have listed as their answer. Okay, they want the answer in kilometers. I apologize, so that is 2,790 kilometers. Once again, the answer you get comes out in SI. You put SI in, you get SI back out. So then we take that number and convert it to kilometers. 2,790.26 kilometers is what they're quoting. All right, one final thing that I want to mention. If we take a look at our units here, I have kilograms squared with kilogram up here. So I've got Newton meters squared per kilogram squared. times kilogram, and then we are dividing by meters per second squared, or I'm sorry, meters squared per second squared. My seconds will get flipped up. Let's see. So writing all of this out in a nice, pretty fashion. Newton times meter squared times kilogram times second squared divided by kilogram squared meter squared. Okay. The meters squared cancels out with that meter squared. 1 kilogram cancels out with that kilogram squared, so I end up with the following units. Again, I do not expect you to do this, but it's still good practice. We have Newton times second squared per kilogram, which is really, really strange, but remember a Newton is made up of a kilogram meter per second squared times second squared divided by kilogram. Kilograms cancel out with kilogram, second squared cancels out with second squared, and this mess is actually equal to meters. It's the same thing as writing meters. It's needlessly complicated, which brings me back to a statement you've heard me say before. If you put SI in, you get SI out. This is why we want to use meters, kilograms, seconds, because whenever we put those into our equations, we no longer have to go through and do this mess every single time. This is why the SI system exists. And this is just the beginning. It's going to get arguably even worse, although not really. Just remember that whenever you're putting in values, you put them in an SI.